Hi everybody, welcome to the lecture of Mathematical Fundamentals in Pharmacokinetics, Part 2. In this lecture, we will do some calculation practice on the fundamental topics of zero order and first order elimination. We will do the calculation of elimination rate constant K for zero order and first order, calculate the half-life, predict the concentration of the drug at certain time, and calculate the volume of distribution. For the zero order elimination, the first practice question is write equation to calculate the elimination rate constant, half-life, plasma concentration, volume distribution for the drug that follow the zero order elimination. So first, let's review about equation to calculate the elimination rate constant in zero order. We call K0 is equal to negative value of y2 minus y1 divided by x2 minus x1. Y is the value of the amount of drug in the plasma, and x is the value of the drug. X is the value of the time that the drug concentration amount is determined in the plasma. Half-life. In the zero order elimination, half-life is equal to 0.5 times initial concentration and divided by the elimination rate constant. Remember, elimination rate constant is always a constant value. It doesn't change, the number doesn't change. However, half-life here, it depends on the amount of drug. For the equation to describe the change of the plasma concentration of drug, CBT equal to C0 minus K0T. CBT is the concentration of drug at any time T. C0 is the concentration of drug, initial concentration of drug, and T is the time you determine the concentration. Volume distribution. Volume distribution is not dependent on the order elimination. Volume distribution mostly is calculated by the equation of dose divided by initial concentration of drug. Write examples of unit for an elimination rate constant of a drug that has a zero order elimination. So remember, the rate constant is the value of rate constant is unchanged. In zero order elimination, you look at the equation here. This equation to calculate the rate constant. So Y is the value of the amount of drug or concentration of drug, and X is the value of the time. So the units for the concentration of drug, for example, if the amount of drug is milligram per this time, for example, is a minute. That example of the unit of the elimination rate constant that follows zero order. If it can be like any the mass of value like milligram or microgram per minute or milligram per hour, etc. That's a unit for the elimination rate constant of a drug that follows zero order elimination rate. The next question is write equation to calculate elimination rate constant, half-life, plasma concentration, and volume distribution for a drug that has a first order elimination. So first we will write the equation to calculate the elimination rate constant. In first order, K is equal to negative value of natural log of y2 minus natural log of y1 divided by x2 minus x1. Half-life in first order equal to 0.693 divided by K. In the first order kinetics, both value of K and half-life as constant. For the plasma concentration of drug, at any time CBT equal to CB0 exponential of minus KT. Volume distribution equals to dou divided by CP0. For the unit of elimination rate constant of the drug that first follow the first order elimination, this is the equation to calculate the elimination rate constant for the first order when in with the value of natural log is a unitless or no unit. So the unit only rely on the time here. So the unit for the elimination rate constant of a drug that follow first order elimination is always like the inversion of the time. It can be like per hour, per minute, or per day, etc. Question: which of the following is a proper unit for the elimination rate constant? A. Minutes. B. Milligram per minute. C. Inversion of hour or per hour. D. Milligram per liter. Remember, in the first order kinetics, the unit of the elimination rate constant based on the equation. Natural log, negative value of natural log y2 minus natural log of y1 divided by 2 minus x1. So the unit for the first order kinetics is always the inversion of time. So C is the correct answer for the first order kinetics. However, in zero order, the unit is a mass per time. So in here, the B, a milligram per minute is a unit for an elimination rate constant of the drug that follow the zero order kinetics. Question: if the elimination rate constant is 0.2 per hour, the percent of drug removed per hour is A. 20%, B. 1%, C. 0.1%, D. 10%. So in this question, you know that the drug has the elimination rate constant is 0.2 per hour. So look at the unit here. It can tell you that the drug follow the first order elimination. So in this one, 0.2 per hour does mean for the first order kinetics, the elimination rate constant demonstrate the percentage of drug is removed per time, removed from the blood per time. So it's here if the K is 0.2 per hour, that means 20% of drug is removed per hour. So the correct answer is A. Question: identify zero order or first order kinetics for the following properties. Dose and serum level has a linear relationship. For this scenario, when the dose change, the serum level will be changed proportionally. For example, if you double the dose, you will have double serum level. In this case, this scenario happened with first order kinetics. Dose and serum level has the non-linear relationship. This means when you change the dose, the serum level doesn't change proportionally. Or when, for example, when you double the dose, the serum level obtained is not doubling. So in this case, it happened with zero order. When the concentration increases, the AUC increases proportionally. The AUC is calculated based on the area under the curve, and this represents the bioavailability of the drug. So it's happened with the first order kinetics. Question: the term rate in pK refers to the change in which of the following measurement over time? A. Drug dose. B. Drug elimination. C. Concentration of drug in plasma. D. Volume of distribution. Remember, the rate in pK refers to the change of speed of drug when you measure the concentration of drug in plasma over time. Question. If a drug that follows first order elimination, the amount of drug eliminated per unit time will A. Remains constant while the fraction of drug eliminated changes. B. Changes while the fraction of drug eliminated remains constant. Remember, in the first order elimination, the unit, the K, the rate as represented is the fraction of drug per time. And the fraction of drug per time, the K is a constant value. So in first order elimination, the percentage of drug removed per time is constant. However, the amount of drug can be changed. So for this equation, the correct answer is B. Question. A drug that follows first order elimination kinetics and one compartment model, which plots can be a curve like A. Plasma concentration versus time. B. Natural log of plasma concentration versus time. Remember, whenever you have a data set of time and concentration of drug, you will plot it in the graph to determine the order of elimination. So first you use the rectangular coordinate. If that's a straight line, so this follows zero order. However, if the data you plot on rectangular coordinate and it's not a straight line, then you take the logarithm of the y bar. The curved line here turn into a straight line. This is a first order. So for this question, if a drug follows a first order elimination kinetics and one compartment, the plots can be a curved line is the one in the rectangular coordinate or the plasma concentration versus time. If it's a natural log of plasma concentration versus time, the plots will be a straight line. Question. A drug that follows a zero order elimination kinetics and one compartment model, which plots can be a curved line. A. Plasma concentration versus time. B. Natural log of plasma concentration versus time. As I mentioned in the previous question, in the rectangular coordinate of the concentration of drug versus time, if it's a straight line, that's a zero order. So if it's a curved line, if you take natural log of this one, it will turn into the curved line. So for zero order, the plots can be a curved line is a natural log of plasma concentration versus time. Question. The amount of drug per unit of volume is defined as which of the following? A. Volume of distribution. B. Concentration. C. Rate. And D. Rate constant. So the amount of drug per unit of volume, for example, milligram per milliliter or milligram per liter, etc. This unit is for the concentration. Volume distribution, the unit should be milliliter or liter. The rate has no unit. For the rate constant, if this is a zero order, it will be the mass per unit of time, for example, milligram per minute, milligram per hour, etc. If it's a first order kinetic, the order will be inversion of time, for example, per hour or per minute, etc. Question. The volume of distribution equals the dose divided by A. Clearance, B. Initial drug concentration, C. Half-life, D. Final concentration. So volume distribution is calculated by dose divided by its initial concentration, or any drug amount divided by concentration of certain time. So the correct answer for this question is B. Question: a 150-pound patient is given with 20 microgram per kilogram of IV drug Y. If a measured serum concentration is 1.1 microgram per milliliter, what is the volume of distribution in liters of the drug in this patient? Round the final answer to the nearest whole number. So the question asks you to calculate the volume of distribution, VD. So volume distribution is calculated by the dose divided by initial concentration. The dose is given in here is 20 microgram per kilogram. Because it's per kilogram, you need to convert to the dose for the patient based on the weight of patient, 150 pounds. This is a pound, this is a kilogram. You need to make sure to convert pound into kilogram to match with the unit. And the dose you will have here is the initial concentration here is 1.1 microgram per milliliter. So you have all the information to calculate volume distribution. However, the important thing is that you need to meet all the requirement of the question, that the final unit of volume distribution in liter, and the final number need to be rounded to the whole number. Okay, now we start doing the calculation. So volume distribution equal dose 20 microgram per kilogram, and this is for 150 pound patient. Then 150 pounds you divided by 2.2, this equal to kilogram, divided by initial concentration, so 1.1 microgram per milliliter. So the units you can cross out kilogram, microgram. So then you will have equal to 20 times 150 divided by 2.2, then divided by 1.1 of milliliter of unit. So volume distribution will be equals to 20 times 150 equal to 3000 divided by 2.2, then divided by 1.1. So you have 1239.694 milliliter. Because the question asks you the volume distribution in liters, so you need to convert into liter. Volume distribution will be equal to 1.239694 liter. That's a long number. So you need to round to the whole number. So from here, the volume distribution will be rounded to 1 liter. So this is the final answer. Question: a patient receiving a dose of 1000 mg of drug X has the following results, assuming one compartment model, or it's case of first order kinetics. With the time after dose, like based on the hours, 2, 4, 6 hours, you have different plasma concentration in milligram per liter, like 100, 67, and 45 milligram per liter. The question: what is the approximate volume of distribution? A, 5 liter, B, 7 liter, C, 10 liter, D, 22 liter. So from this question, from this data, you need to calculate the volume of distribution, and we know that volume of distribution is equal to the dose divided by initial concentration. So you have the dose here is 1000 milligram, but you don't have the initial concentration. Look at the data. The data at the time after dose, 2 hours, you have 100 milligram per liter. So if you use this value, the estimated volume distribution will be inaccurate, because the time is the concentration you get here is not initial concentration. Because at that time, if you take like the dose 10,000 milligram divided by 100 milligram per liter, you have 10 liter. That's not accurate volume distribution. So in this one, the volume distribution will be different. So in this case, you need to calculate or look for the CB0. And because this is a one compartment model, you know that one compartment model equation to demonstrate or describe the concentration of drug over time is a CBT equal CB0 exponential minus KT. So if you know CBT, you know K and know T, then you can know the CB0, and then you can plug in here to calculate. So how to calculate CB0 here? So in this case, for any, you have three time points. So you can select any two time point, any time point to calculate the CB0. So for if I select CB at here like 100, if I select like 100 milligram per liter, I have CB0 times the exponential minus KT. T here, that should be 2 hours. However, I still need to calculate the value of K. And in the first order kinetic, how to calculate K? K will be equal to natural log, negative values of natural log of y2 minus natural log of y1 divided by x2 minus x1. So in the three time points here, I can select any two time points to calculate the K. For example, I select this one, the two time point. So I have x1 and I have y1, I have x2 and I have y2. So in this case, the K will be negative value of natural log of my x2 is 67. Subtract natural logs of y1 of 100 divided by x2 4 minus x1 2, and the units here is hour. So then I have the negative value of natural log of 67 equal 4.2046. Subtract natural log of 100 equal to 4.6051 and divided by here 2 hours. So the K I will have equal to K equal to 0.2002 per hour, or equal to K equal to 0.2 per hour. So when I know K, I can use any CBT to look for CB0. For example, if I look at the CBT 100 here, so I have 100 CBT 100 milligram per liter. I will use this equation equal to CB0 exponential minus K. I have K 0.2 per hour time. The time here, because you 100, the time here should be 2 hours. And these units can cross out. So finally, I will have 100 milligram per liter equal to CB0 time. I will calculate here separately exponential minus 0.2 times 2. So this means exponential minus 0.4. This equal to 0.6703. So CB0 will be equal to 100 milligram per liter divided by 0.6703, or CB0 will be equal to 149.186 milligram per liter. Now I use this value CP0, I plug into this equation. So I have volume of distribution will be equal to dose 1000 milligram divided by 149.186 milligram per liter. Our volume distribution will be equals to 6.703 liter. So the volume about 6.703 liter. So look at the equation here, A, B, C, and D. The most correct answer is B. Question. Drug concentrations are measured in plasma and assume that the concentrations are the same as those in tissues because the drug concentration cannot be practically measured in specific tissue. That is true. Why? Because in practice you cannot measure the drug concentration in tissue, and only way is to measure the concentration in plasma, and you assume that the drug concentration in plasma represent the drug concentration in the tissue. Question. In a pharmacokinetics study, a patient received a 475 milligram dose of an experimental drug at 7 p.m. with serum drug level monitored hourly for 24 hours. The investigator assumes that 8% of the remaining of drug is eliminated per hour across all the recorded time points. What is the order kinetics of this drug? What equation can be used to calculate the elimination rate constant, half-life, and drug concentration, respectively, for this drug? So look at the question. So what data you have? This is a patient received 475 milligram dose of drug at 7 p.m. So that's something you hear. But what's the equation? What the question? They ask what's the order kinetics of this drug. So focus on this question. Order kinetics, you have zero order or first order. In zero order kinetic, is the amount of drug is removed per time is constant. And in the first order kinetic, the percentage of drug is removed per time is constant. So look at the data, what you have. Assume that 8% of the remaining drug is eliminated per hour across all recorded time points. So that means all the time 8% of the drug is removed. So in this case, percentage of drug is a constant. So to answer the question, order kinetic, so the question, first order kinetic, that should be first order kinetic for this drug. So for the first order kinetic, what equation can we use to calculate the elimination rate constant? For first order, K equal to negative value of natural log of y2 minus natural log of y1 divided by x2 minus x1. Y is a represent for the drug concentration or drug amount, and x is the time value. For the half-life in first order kinetic, half-life is equal to 0.693 divided by K. The equation to describe the drug concentration over time, CPT equal to CP0 exponential minus KT. Question. If a dose of gentamicin is administered and a peak plasma concentration is 6 mg per liter after the infusion is completed, and a concentration of 1.5 mg per liter is obtained 4 hours later, what is the elimination rate constant of the drug? Route the final answer to the nearest hundredth. So what's the question asked you to do? What is the elimination rate constant? So you need to calculate K. it depends on the order elimination process, zero order or first order. You will have a product equation to calculate. So in here is gentamicin. Gentamicin is well known is a first order drug. So then you will have the equation to calculate case will be natural log, negative value of natural log of y2 minus natural log of y1 divided by x2 minus x1. So in this case, this is the infusion. It takes infusion drug, and when it's reached the peak here, and it stop infusion, the peak here is 6 milligram per liter. And then when it stop here, the drug concentration will be reduced due to the elimination process. So, and then after the stop, after infusion stop, if I call here is 0, it's a 4 hour later, it's 4. Then the concentration obtained is 1.5 milligram per liter. So then we can calculate the value of K. If I call this one is x1, I have is y1. I call his x2, I have y2. So using this equation to calculate K equal to natural log of y2. That means natural log of 1.5 minus natural log of y1. Y1 is natural log of 6 divided by x2 minus x1 is between them is 4 hours. So you have 4 hours here. So equal to negative value of using the calculator to calculate natural log of 1.5. This is 0.4054. Subtract natural log of 6. Natural log of 6 is 1.7917 divided by 4 hours. So K will be equal to, in this case, because negative value here, you will take 1.7917, subtract to 0.4054. Then you divide it by 4. Then you have K is equal to 0.346575 inversion of hour. And rounding to the nearest hundreds here. So K will be equal to 0.35 per hour. This is the final answer. Question. Drug X is IV or intravenously given to 2 patients. 2 plasma concentration are then determined, and the slope of the plasma concentration versus time curve is calculated. Determine which patient, A or B, has the smaller elimination rate constant. So we have patient A and patient B. The slope of plasma concentration versus time curve. So for patient A, like this elimination rate. So for patient A, the slope is 0.55. Patient B, the slope is a negative of 0.23. So remember the elimination in calculating the elimination rate constant, we depends based on the slope. So if the slope of a drug is higher, when the slope of value, the absolute value of the slope is higher, that means the drug is eliminated faster. So in this case, if the slope is 0.55, so the elimination rate constant is a negative value of slope. So in this case, the K will be equal to 0.55. In this here, K will be equal to 0.23. So look at the two values. The elimination rate constant K of patient A is higher, 0.55 higher than the K of 0.23. So in this case, the elimination rate constant of the patient A is larger than elimination rate constant of patient B. Or we can say that a patient B has the smaller elimination rate constant. Question. In a pharmacokinetic study, a patient received a 500 milligram dose of an experimental drug at 5 p.m. and serum drug concentrations were sampled every hour over a 12-hour period. The investigator determined that the drug is eliminated at a rate of 0.25 microgram per hour across all the observed time points. What is the order kinetics of this drug? What equation can be used to calculate the elimination rate constant, half-life, and drug concentration, respectively, for this drug? So again, to determine the order kinetics of this drug, you need to know the elimination rate constant. So for this one, it's the drug is, look at this information, the drug is eliminated at a rate of 0.5 microgram per hour. So elimination rate constant, K for this one is 0.25 microgram per hour. So over time, the amount of drugs removed per hour is unchanged, and that's 0.25 microgram. So this one will tell you that the drug follow zero order kinetics because the amount of drug is removed per unit of time is constant. For the next one, to answer equation to calculate elimination rate constant for the here is K0 for zero order. So the K is equal to negative value of y2 minus y1 divided by x2 minus x1. Y is the value of concentration or amount of drug in the plasma, and x is the value of the time. The half-life equal to 0.5 times initial concentration and divided by the K. Elimination rate constant of the zero order. Question. Following the administration of a 300 milligram dose of a drug X, the elimination rate constant was identified as 0.3 per hour. Calculate the half-life in hours of the drug. Route the final answers to the nearest hundredth. So in this one, you see you have elimination rate constant of K is equal to 0.3 per hour. So from the unit here, tell you that the drug follow the first order kinetics. In the first order kinetic, the half-life is calculated by 0.693 divided by K, or equals 0.693. K is 0.3 per hour. So the half-life will be equal to 0.693 divided by 0.3 is 2.31 hour. The question asks you to route the final answer to the nearest hundred. It's already nearest hundred with the value 2.31 hours, so you don't need to do anything. Question. If a drug has an elimination rate constant of 0.564 per hour, what is the half-life? It's similar to previous question. The data here with the unit inversion of hour tell you that the drug follow the first order kinetics. So the half-life, first order of elimination, half-life is equal to 0.693 divided by K is equal to 0.693 divided by 0.564 per hour equal to 0.693 divided by 0.564 per hours, or the half-life is equal to 1.2287 hours. So in this question, they don't ask you any routing. Just in case it's like routing to the nearest hundred, that will be equal to 1.23 if the nearest hundred. Question. Drug X is given by IV administration to two patients. Two plasma concentration are then determined, and the slope of the plasma concentration versus time curve is calculated. Determine which patient, A or B, has the Richter elimination rate constant. So again, you have the slope of patient A is 0.55, the slope for patient B is 0.23, and you know that the K elimination rate constant is the negative of the slope. So in this case, the K value for this one is 0.55, and the patient here is 0.23. And the Richter K value, the Richter elimination rate constant, of course. So then in this case, patient A has the Richter elimination rate constant. Question: drug X is given to two patients, and two plasma drug concentration are then determined for each patient. Determine which patient has the greater elimination rate constant, assuming the drug follow a first order elimination. So you have the set of data of the different time point 8 hours and 16 hours. The plasma drug concentration in patient A is 22, then 5 milligram per liter. Patient B is 30, then 8 milligram per liter. So look at the question. The question asks you to compare about the elimination rate constant of patient A and B to see which one is greater. To compare that, you need to know the value of K, because it's follow the first order elimination. So you know that the elimination rate constant is calculated by the equation K is equal to negative value of natural log of y2 minus natural log of y1 divided by x2 minus x1. If because here is x1, then I have y1 for the patient A. x2, I have y2 value for the patient A. And similarly, I will have here y1 for patient B and y2 for patient B. So then, based on the set of data, I will calculate the elimination rate constant of each patient. For patient A, now I calculate. K is equal to natural log of y2, I have natural log of 5, minus natural log of y1 or 22. x2, I have 16, minus x1, 8 hour. So K equal to negative. Natural log of 5 is 1.6094 minus natural log of 22 is 3.091 divided by 6 minus 8 is 8 hour. So K is equal to 0.1852 per hour. This for the patient A. Now for patient B, K is equal to negative value of natural log of y2 a minus natural log of y1 is 30 and divided by 16 minus 8 hour. So K here is equal to negative value of natural log of 8 is equal to 2.0794. Natural log of 30 is 3.4011 in per 8 hour. So K is equal to 0.1652 per hour. So in this case, when you compare the values, so patient A has a greater value of elimination rate constant. Question: a patient receives a dose of drug B. Plasma concentrations were 22 and 15 milligram per liter at 24 and 48 hours after infusion, respectively. Determine when the concentration would reach 10 milligram per liter. assuming the drug follows first order elimination. In this question, you are asked to determine the time or predict the time for the drug to reach a certain concentration, 10 milligram per liter. So let me explain a little bit about the scenario. So this is infusion. It's in infusion. It takes time for the drug, and when it reaches a certain concentration, and it stops here. If I call the stop here, like for example, I call 0, and then after the drug is stopped infused in here, the drug concentration start declining like this. So if I call the stop, the time point that stop infusion is 0, then all the time like 24 hours after infusion and 48 hours after infusion, the drug concentration is determined. At 24 hours, based on the information, the concentration is 22 milligram per liter, and as 48, the drug concentration is 50 milligram per liter. So you are asked to calculate or to estimate the time when the drug concentration will go to 10 milligram per liter. What's the time point here? This kind of concentration is very useful in determining like certain drug with the certain concentration. Like you need to maintain the MEC, the drug should be within the therapeutic window, and whenever the drug reach to certain MEC, that means minimum effective concentration or certain concentration, they need to give the next dose. So in this case, estimate the time to reach that certain concentration. That helps you to determine when the patient can be given the next dose of the drug. So it's very helpful in clinical pharmacokinetics. Now we come back to calculate this calculation for this scenario. This is for first order elimination. Whenever you are asked to calculate or to predict the concentration or predict the time, you always use the equation CBT is equal to CB0 or C0 initial concentration times exponential minus KT. So in this scenario, you are asked when the drug is a 10 milligram per milliliter, that's CBT. Then you need to calculate the T. So in this case, you don't have CB0. You don't have the value of K, and you need to look for T. So there are three parameters you need to look for from the data you are given. So first, we will calculate K here. Then we calculate CB0, and we know K and CB0. We plug in to this equation. Then we can find out T. To calculate K, this is a first order elimination. With any two time point, you can calculate the K. And we know that K is equal to a negative value of natural log of y2 minus natural log of y1 divided by x2 minus x1. And K is equal to natural log of, if I call here x1, then I have y1. If I call here x2, then have y2 here. So natural log of y2 or natural log of 15 minus natural log of y1 or natural log of 22 divided by 48 minus 24 hour. So K is equal to negative value of, so natural log of 15 is equal to 2.708. Natural log of 22 is equal to 3.091 and divided by 24 hours. So from this equation, I have the K value is equal to 0.01596 per hour. So now I have value of K. The next parameter I need to look for is the CB0. How to calculate CB0? We use the same equation of CBT equal to CB0 exponential minus KT, But in this case, CBT, I will select a T and CBT that I already know from the data. For example, if I select the time point at 24 hours, the CBT at 24 hours is, if CBT at 24 hours, I have 22 milligram per liter is equal to CB0 exponential minus K. I just calculate K here. K is 0.01596 per hour, and time T, because at 24 hours I select 24 hours, T will be 24 hours. So from here I will have 22 milligram per liter is equal to, I will calculate the whole group here, will be equal to CB0 times 0.6818. So using calculator, then I have the value of CB0 is equal to 32.2676 milligram per liter. So I have CB0, I have K. So now I just saw out the T. Okay, sorry for the crowded here. So now I calculate the T. I use again CBT is equal to CB0 exponential minus KT. So then CBT I have 10 milligram per liter equal to CB0, we just calculate 32.2676 milligram per liter times exponential minus K. K is 0.01596 per hour times T here. So that's you have the equation. Now next we need to calculate, we just cross out the unit here. So then you will have 10 equal to 32.2676 times to exponential. You need to calculate the whole here. So exponential minus 0.01596 times T, and the T here is an hour. So then I will calculate this one and this one first. So I put 10 divided by 32.2676, then I have 0.3099 equal to exponential minus 0.01596 T. To solve the T, I will take the natural log of the two sides. Natural log of 0.3099 equal to minus 1.1715. Then because I take natural log of exponential here, I will minus of 0.01596 times T. Remember the T value here is an hour. So solve the problem T from this equation. I have T is equal to 73.402 hours. So I can answer the question. So after around 73 hours or 73.402 hours, the drug concentration would reach a 10 milligram per liter. Question: determine the plasma concentration of a drug 24 hours after a peak level of 10 milligram per liter is observed if the elimination rate constant is 0.05 per hour. So for this kind of question, you are asked to predict the plasma drug concentration at a certain time, and unit from here up, the elimination rate constant will tell you that the drug follow the first order kinetics. So in the first order kinetic, to predict the concentration of any drug, you always use the equation CBT is equal to CB0 exponential minus KT. So CPT at 24 hours you need to look for equal to CB0. This means initial concentration or the peak level. Here you have the peak level. Here is also the initial concentration of 10 milligram per liter time exponential minus K. You have the value K here, 0.05 per hour. And the T, because drug after 24 hours, so you have time to 24 hours. And these units can be crossed out. So from equation, you have CBT is equal to 10 milligram per liter. Then you need to calculate the exponential of this one. And exponential minus 0.05 times 24 will be equal to 0.30119. So then you have CPTs will be equal to 3.0119 milligram per liter. So after 24 hours, after the peak level is obtained, the plasma drug concentration is estimated to be about 3.0119 milligram per liter. Question: the peak plasma concentration of gentamicin is 8 milligram per liter, and the patient elimination rate constant is 0.25 per hour. What will be the concentration of the drug 8 hours later? Route the final answer to the nearest 10. In this question, you are asked to predict the concentration of gentamicin 8 hours after the peak. So and because you know that from the unit and also gentamicin follow the first order elimination, we can use the equation CPT is equal to CP0 exponential minus KT to predict the concentration of the drug after 8 hours. So CPTs will be equal to CB0 at the peak. We have here is the 8 milligram per liter time exponential minus K here 0.25 per hour, and time to T they ask at 8 hours later, so time 8 hours. So cross out the unit here. So then you have CPT is equal to 8 milligram per liter time, then you calculate the group here. S will be equal to 0.1353, or the CPTs will be equal to 1.0827, and routed to the nearest 10, then you have 1.1 milligram per liter. Question: a drug has the peak plasma drug concentration of 10 milligram per liter and follows first order elimination. What is plasma concentration of the drug 24 hours after the peak if the elimination rate constant is 0.05 per hour? Route the final answers to the nearest 100th. So in this question again, you are asked to predict the drug concentration at certain time T, and then after like 24 hours after the peak. So then you use the equation CPT is equal to CP0 exponential minus KT. Then you're looking for the CPT at 24 hours, so CP24 will be equal to the peak level. CP0 is 10 milligram per liter time exponential minus KT, and you have value K here 0.05 per hour, and time T because you look for 24 hours time 24. So CPT or CP24 E equal to 10 milligram per liter time, then you calculate the group here. The group here is equal to 0.30119. So then, remember this 24 hour here, so you can cross the unit. So then Cp 24 will be equal to 3.0119 milligram per liter. And if you round to the nearest 100, you will have Cp 24 will be equal to 3.01 milligram per liter. Question: for a drug that has an initial plasma concentration of 120 milligram per liter and a half-life of 3 hours, what would the plasma concentration be 12 hours after the initial concentration? Round the final answer to the nearest hundredth. In this question, again, you are asked to predict the concentration of drug in the plasma at certain time t, and specifically here is at 12 hours. The drug follow assume that the drug follow in the first order kinetics, then you have CBT predict equal to CB0 exponential minus KT. And in this here, you look for CP12, that means 12 hours after the initial concentration. CB0 or initial concentration, you have here 120 milligram per liter. Then time to exponential minus KT. You don't have K in this problem, but you have the value of half-life. So half-life is equal to 3 hours. And for the first order elimination, half-life is equal to 0.693 divided by K. So then you have K is equal to 0.693 divided by half-life. And for this scenario, you have K is equal to 0.693 divided by half-life. Here is 3 hours. Or K is equal to 0.231 per hour. So from the value K here, I will bring it to this equation. So CB12, I mean after initial 12 hours after initial concentration, is equal to 120 milligram per liter times exponential minus K. K, I just have the case here, is 0.231 per hour. Time T, because we're looking for 12 hours after that, so that means time 12 hours. Cross out the unit, then you calculate the value of the group here. Then I have CB12 is equal to 120 milligram per liter time to the value of the group or exponential here is 0.062536. So then I have a CB12 is equal to 7.50432 milligram per liter. Rounded to the nearest hundredths, I have CB12 is equal to 7.50 milligram per liter. Question: fill in the blank to complete the sentence. VD or volume of distribution could be, you have small or large when you have 4 scenarios. So the first one, volume distribution could be small or large when the drug is extensively distributed to the tissue. So when the drug is extensively distributed to the tissue, what happens with volume distribution? Remember, volume of distribution is a hypothetical volume that describe or demonstrate or to describe the drug distribution, the volume that the drugs like is distributed in, and it's a hypothetical volume. So if the drug is extensively distributed in tissue, more drug in these tissues, the volume to contain the drug is large. So in this case, the drug is extensive distributed in tissue, the volume of distribution is large. The second scenario, when the drug has a high affinity to the tissue, so this means the drugs will bind to the tissue and stay long there. So it's make the volume to contain the drug, or for the long time and large. So in this case, the volume distribution will be large too. Drug has a high binding with plasma protein. So when the drug has a high binding with plasma protein, what happens? Remember the common equation to calculate the volume of distribution is a volume of distribution is equal to the dose divided to initial concentration. So if the drug has a high binding with plasma, that means the drug stay in the plasma and it cannot distribute to the tissue more, because with the binding to plasma protein, with the structure, bulky structure, and with the property or physical chemical properties of the drug with the protein, the drug cannot be distributed to tissue. So in this case, high concentration of drug will be in the plasma. For example, in this case, you look if a high concentration of drug in the plasma, if a CB large is high here, it makes the volume distribution will be small. The next scenario is that the drug has high concentration in the plasma. The same as scenario C. When the drug has a high concentration in plasma, then the high concentration here, the volume of distribution value will be small. So we already have some practice on the general basics of calculation to review the mathematical fundamentals in pharmacokinetics, or mostly to review the zero order, first order, to calculate elimination rate constant K, volume of distribution, half-life, as well as to predict the drug concentration at certain time. Thank you for your attention.